We can now move to the next industrial paper. The speaker is Jeunen Olivier. Okay, welcome. And it is, the topic is somehow related because we are talking again about A/B testing, powerful A/B testing metrics and where to find them. Thanks.
Yes, hello everyone. So I will be talking about what it looks like when you do an A/B test. So usually you first choose a certain North Star metric, which is really the main thing that we are going to care about as a business. So this can be something like user retention or long-term so revenue, like these things. Then we have a certain null hypothesis. We're going to have our variants shipped in production. We're going to wait for a few weeks maybe. We have data. Then we can use that data to compute z-scores and p-values, and we compute them, and when the p-value is low, we profit, right? All of that sounds amazing, but that's really not how it works in practice very often. So the metrics that we really care about are typically long-term metrics, and so we have to wait a while to be able to actually compute them. We then really have to wait a while to get data, but time is money, and we don't really like waiting. Then when we get the data and we compute the z-scores and the p-values, very often it's a high p-value. And so we don't really get to profit, right? We can just sort of try again and hope things work better next time. Or we can look at different metrics than just the North Star metric. So really often we're in this sort of situation where you have a certain estimate of the sort of treatment effect in your A/B test, maybe on the North Star metric. We're not able to make any statements about whether it's positive or negative, but we have a bunch of other metrics that we also track, right? Maybe we have fewer sessions that are slightly longer, we have maybe fewer engagements, but more time spent on the platform. And so then the question really becomes whether this is a good A/B test, whether this is a sort of positive outcome or not. And so that question is just, well, which of those metrics matter, right? Which are the metrics we should really be looking at and which should we not be looking at? And so I think that, very often we see these types of things in industry, and very often there's heated sort of discussions about, when there's more time spent on the app, that's amazing, but then there will be other people who say, whoa, wait a minute, if you have less engagements, that's going to be an issue. And so maybe we should just really try to answer this question with data. And so the data that we have is typically just all of the past experiments that we've ran on the platform. And so we collected a data set of a few hundred past experiments, and you can look at them and you can sort of classify experiments into 3 different classes. There will be experiments with known outcomes where we know for a fact that the North Star metric moved significantly, and so A is better than B, or B is better than A, but then we just relabel what B and A is. And so that's the first class of experiments that's really important. Then secondly, we will have a lot of experiments where we're not really sure what happened, right? So we have a lot of metrics that are moving, but the North Star, we're not really able to make any statements about whether A is better than B. And then a third class of experiments are simply sort of AA outcomes, where we can sort of resample these from the data by essentially the 2 variants are doing the same, and we can do this to measure things like sort of type 1 errors. And so what we sort of typically care about then is the power and the sort of sensitivity of a metric. So we really want to measure something like the z-score, and so there's a lot of Greek letters on the slide here, but this is simply for a given metric, for a certain variant A and B, it's a difference in means divided by the total standard deviation. So this is nothing more than a signal-to-noise ratio, and we can use that to see whether metrics are actually useful, whether they have a lot of signal or a lot of noise. And so the z-score is typically then reformulated into a p-value, and if the p-value is lower enough, if the p-value is lower than a certain confidence level we choose, then we say the result is significant. So what do we want from our metrics? Well, typically there's 3 types of sort of errors that you can make with a metric. The first one is a type 1 error. And so we can't have none of those, but we can keep them sort of manageable, right? So a false positive is what you get when you have an AA experiment, where you have a p-value that's actually saying that there's a difference. And so when things are set up correctly, you sort of get a few sort of guarantees by the central limit theorem that if you do everything right, you should be able to get an expected level of type 1 errors. And this is something we can now check with the data that we have. We can look at all of the AA experiments, and for all of those where the Z-score is too high or the p-value is too low, all of the AA experiments where we have a significant result, that's a problem. And we can count this, and we now know for all of our metrics whether we're actually able to manage those type 1 errors. We also have type 2 errors, a false negative, where for all of the experiments that actually had a known outcome, but also those with an unknown outcome, we know that there's a difference between the two variants, so we want to know to be able to say which of those is better. So we can just look at that data. We can look at all of the past experiments that we have. We can look at in which cases the Z-score was too low or the p-value was too high, and we can count that, and we can put all of that into a table and figure out which metrics are useful. And so typically, these are the two most common errors that people talk about. But you also have a type 3 error or a sign error. And this is really a problem. These are situations where we, for example, see the North Star saying very, very clearly A is better than B, but this metric moved in a different direction. B is better than A. And so these are the metrics that we would typically not want to use for like making a certain decision when the North Star is non-significant. And so these are also things we can simply measure from the data. We look at all of the past experiments with known outcomes. When there is a significant difference in the wrong direction, that's a type 3 error, and these metrics are going to be automatically disqualified. Great. So we now have a way to figure out which metrics are useful, and we can use this to actually make our experiment pipelines much more efficient. So here on the x-axis you have a changing value of alpha, so how many type 1 errors you're allowing to exist. On the y-axis you have type 2 errors, and so if we just look at a single metric, for example DAO, which is really quite important for the growth of a platform typically, we get fairly high type 2 errors. But we also have a few different metrics that we can use in conjunction with them, and we can validate them. We can make sure that we've never actually empirically observed a type 3 error. And so maybe if we run an experiment and DAO is non-significant, but one of these other metrics is significant, we can use that to make decisions instead. And so this means we can actually get significantly reduced type 2 errors at a constant sample size. And a different way to look at this is, well, maybe I'm actually fine with the level of type 2 errors that I have. And then you would actually be able to use this to get significantly reduced sample sizes at a constant statistical power. So that's what we did at ShareChat. We're using this to figure out which metrics are important and which ones are less important. And it makes it a lot easier to have an experimental discussion where we can talk about data instead of about opinions. So that's my talk. I'd be very happy to answer any questions.
Thanks, thanks Olivier. Well, there are a couple of questions online. The first one is, in other scientific domains like psychology or medicine, A/B testing is widely used. So the question is, if in RecSys we should just use the same power analysis as used in other scientific domains.
Right. Yes, but then I'm not really well versed in other scientific fields, but I would assume you would then look at a single metric, right? And so you can look at how much power we would want for something like the North Star. We want to measure long-term revenue, but still very often you will end up with experiments where you don't really know what to do because the metric isn't really moving. There's a bunch of other metrics moving, and we still want to make a decision as a company. So yeah. Okay,
so thanks. There are other questions coming. I think we have time only for one question. So how does your approach account for the family-wise error rate when evaluating multiple supporting metrics across numerous different experiments?
That's a very good question. We use a sort of Bonferroni correction. So there's no place in a two-page paper to have a plot for that, but we ensure that we get the right type 1 error rate.
Okay, thanks again,
Thank you.
Olivier, for your presentation. We can thank the speaker.